Assalamualaikum and hi everyone. Okay, so in this video I'm going to show you the two types of reaction mechanism for the reactions of alkene, which is the first one is hydrohalogenation of alkene and the second one is acid-catalyzed hydration of alkene. Okay, so before we proceed further with the reaction mechanism, I would like to introduce to you about Markovnikov rule. So Markovnikov rule states that, okay, for hydrohalogenations of alkene, X, which is your halogen, should be added to the carbon atom which has less hydrogen atom. Okay, so X will be added to the carbon atom of the C double bond C that has less hydrogen atom. Okay, so this is if we are doing hydrohalogenation. Okay, if it's acid-catalyzed hydrations of alkene, okay, so the OH, okay, will be added to the carbon atom of the C double bond C that has less hydrogen atom. Okay, so let's proceed with the first example. Okay, so in hydrohalogenation process, okay, there are two steps mechanism. Your alkene is a source of nucleophile. Okay, so this is your nucleophile. Okay, so this double bond will attack your hydrogen because your hydrogen is partially positive because it's more electropositive, whereas your bromine here in your hydrogen bromide is more electronegative. Okay, so the double bond, okay, the electron from your double bond will attack your hydrogen and the bond between the hydrogen and bromine will break. Okay, so the bromine will take the electron in the bond. Okay, so we are making this carbocation ion. Okay, so we are making this carbocation ion. Okay, so I'm making secondary carbocation ion because that is more stable and it obeys that Markovnikov rule. Okay, and a halide ion, which is your bromide ion. So your bromide ion contains 8 electrons, okay, with a negatively charged. Okay, so in the second step, okay, my bromide ion, which is now my nucleophile, okay, so this bromide ion will attack the positively charged of the carbocation ion to form bond. Okay, so an arrow should start from the negative charge and it attack the carbon positive center. So as a result, we have this molecular structure, okay, structural formula, and Br is added here. Okay, so that is your new alkyl halide. So you're going to learn how to name this alkyl halide when you learn chapter 7 later on. Okay, so let's go for another example. Okay, so as always, we always start with formation of carbocation ion and halide ion. So your electron from your double bond, okay, because your alkene is a nucleophile because it has C double bond C, which is a center with electron rich center. So it will attack the hydrogen in your hydrogen chloride because your hydrogen is partially positive, whereas your chlorine here in HCl is partially negative. Okay, so an arrow, double-headed arrow attacking the hydrogen. Okay, so in this reaction, it involves heterolytic cleavage. Okay, and then, okay, the bond between this H and Cl will break and both of the electrons at the bond between this H and Cl will go to your chlorine atom to form chloride ion, okay, which is your new nucleophile. Okay, so your chlorine will attack the carbon in your carbon-carbon double bond that has less hydrogen. That means my positive here will be at the highly substituted carbon. So I'm making this secondary carbocation ion with a chloride ion, okay, as my new nucleophile. Okay, so the nucleophile, the chloride ion that I made throughout my first step reaction, okay, will be useful to attack the center of my carbocation ion. Okay, so to form your alkyl halide. Okay, so this is another new alkyl halide. Okay, so let's move on to another example. Okay, so in this one, I want to make it in a long step processes instead of small steps, okay, to show the reaction mechanism for the electrophilic addition of my HBr into my alkene. So always start by the electron from the double bond attacking my H of my HX hydrogen halide, okay, and then the bond between the hydrogen and the halogen will break and everything goes to the halogen so that it can form halide ions, okay. So this is my carbocation ion. So I need to make more stable carbocation ion, so therefore my plus charge will be at the secondary carbon. Sorry, it should be at the tertiary carbon, plus my bromide ion as my nucleophile, okay, with 8 electron. Okay, in the next step, okay, the negatively charged from my bromide ion will attack the positive center of my carbocation ion. So we are making a new bond between the carbocation ion with my halogen. Okay, and let's move on to another example. Okay, so this one again, okay, from the double bond it will attack the hydrogen in your hydrogen chloride, and the bond between the hydrogen and chlorine will break. Okay, so all the electron in the bonding will go to the chlorine atom. Okay, plus Cl with minus, okay. So the negatively charged of your chloride ion will attack the positive center of your carbocation ion, and now we are forming bonding between the carbocation ion with the chlorine. So we are making alkyl halides. Okay, so I have the last example. So in this one again, okay, from my carbon-carbon double bond, I attack my hydrogen here, and the bond will break heterolytically to the bromine atom. Okay, if you want to label, this is partially positive and this is partially negative. Okay, so we are making this carbocation ion. Okay, so the carbocation ion should be a higher degree of carbocation ion. So in this one, instead of primary, we goes to tertiary carbocation ion plus our halide ion, okay, with a negatively charged. Okay, so this halide ion will attack the positive center of your carbocation ion, okay, heterolytically, so that it will form your alkyl halides. So this is your alkyl halides, which in this hydrohalogenation, it follows and obeys the Markovnikov rule, where the halogen should be added to the carbon in your carbon-carbon double bond, which has less hydrogen, or a carbon in the carbon-carbon double bond which is highly substituted with alkyl group. Okay, so I'm going to leave you with an exercise where you need to outline a mechanism for the electrophilic addition of your hydrogen chloride to 2,2-ethyl to butene. Okay, let me guide you with the structural formula of your 2-ethyl to butene. So butene is 4 carbon, 1, 2, 3, 4, and we have carbon-carbon double bond at carbon number 2, so 1, 2, so here is your double bond, and at the carbon number 2 you have ethyl group, so CH2, CH3. Okay, so try to choose the reaction mechanism for electrophilic addition of your hydrogen chloride for this chemical compound. Right guys, so now I'm going to show you the reaction mechanism for acid-catalyzed hydration of alkene to produce alcohols. Okay, so this reaction will obey Markovnikov rule. Okay, where in the Markovnikov rule, okay, your Markovnikov rule states that the OH group will be added to the carbon, okay, to the C in your carbon-carbon double bond which has less hydrogen atom. Okay, alright, so this hydrations of alkene is addition of water in the presence of dilute sulfuric acid. That's why we name it as acid-catalyzed hydration, because that diluted sulfuric acid acts as the catalyst for the reaction. Okay, so first, there are 3 steps, okay, in the acid-catalyzed hydrations of your alkene. So the first step will be the formation of carbocation ion. So H3O plus, which comes from your sulfuric acid, okay, so the double bond here, okay, from your alkene will attack the hydrogen of your H3O plus, okay, so the bond between the hydrogen and O will break heterolytically and all the electron will be accepted by the oxygen. So we are making a carbocation ion, okay, and elimination of water. Okay, so plus H2O. So this water will be used in the next step, okay, which is to form protonated alcohol. Okay, so the water will attack your so the water released from the first step, okay, has 2 lone pairs of electron. So one of the lone pairs of the electron will attack the positively charged carbon of your carbocation ion to form a protonated alcohol. Okay, so it will look like this. OH with a plus charge on the oxygen atom. So we name it as one as your protonated alcohol. Okay, since we want to make alcohol, so that means I need to eliminate one of the hydrogen in your protonated alcohol, so it will form alcohol, okay, with OH group and no plus charge. Okay, so we are finally at the last steps of your acid-catalyzed hydrations of your alkene, okay, where in the third steps it involves the elimination of H+. Okay, so we're going to use water molecule with 2 lone pairs of electron. One of the lone pairs of electron, okay, will attack the hydrogen in your OH, okay, in your protonated alcohol, and this bond between the oxygen and hydrogen will break heterolytically, so both of the electron will go to the positive center oxygen. So we regenerate our H3O plus, which is our acid, okay, since this one acts as a catalyst, so that means it's not used up in the reaction, and we reproduce it again at the end of the reaction, so it can be used for another acid-catalyzed hydration, plus our alcohol. Okay, so that is. Okay, so I'm going to show you with another example. Okay, so it involves again 3 steps, which is the first one, formation of carbocation ion. So it always starts by the electron, okay, from the double bond here is going to attack the positive hydrogen, okay, and this OH bond will break heterolytically and both electron goes to the oxygen atom here. Okay, so we are making a carbocation ion. Please make sure, bear in your mind, okay, you need to make sure you form a higher degree of carbocation ion because it's more stable, plus water molecule. So this water molecule released from this first step will be used in the second step, okay. So the lone pair of electron from your water molecule here will attack the positive center of your carbocation ion, so we are making a protonated alcohol. Okay, don't forget the plus charge on your oxygens of your protonated alcohol. Okay, so move on to the last step. Okay, so your last step will be the eliminations of water, because I'm going to continue from here. Okay, from here. Okay, so plus water molecule. Okay, so the lone pair of electron from your oxygen will attack the hydrogen in your protonated alcohol, and this bond between the oxygen and hydrogen will break heterolytically, so both of the electrons will go to the positive center oxygen. So finally we regenerate our hydronium ion, which is comes from your acid, okay, plus your alcohol. I have the last one. Okay, another example. Okay, so in this one I'm going to make it into a continuous reaction mechanism, continuous steps of reaction mechanism. Okay, so first start by forming carbon-cation ion. So the carbon-carbon double bond will attack the hydrogen of your hydronium ion. So and then this bond will break heterolytically. So we're going to form carbon-cation ion. Okay, and release water molecule. So this water molecule with two lone pairs of electron will attack the positive center of your carbon-cation ion to form the protonated alcohol. Okay, so OH. Okay, so with a plus charge on the oxygen atom. Okay, so another water molecules with two lone pairs of electron will attack this hydrogen of your protonated alcohol, so that the bond between the oxygen and hydrogen will break and both electrons can go to the positive center of the oxygen in your alcohol, protonated alcohol. So at the end we will form an alcohol, and your H3O plus is regenerated at the end. Okay. So last example. Okay, so I have here one butene as usual. Okay, from the carbon-carbon double bond it will attack this hydrogen. Okay, and then this OH bond will break and both of the electron will go to the positive center oxygen. Okay, so we are making your carbon-cation ion. Okay, so plus charge here and release water molecule. So the lone pair of electron from your water molecule will attack the positive center of your carbon-cation ion to form your protonated alcohol. Okay, so always remember if it's a protonated alcohol, so that means it should have plus charge on your oxygen atom. Okay, so another water molecule with two lone pairs of electron will attack your protonated alcohol, attract the hydrogen of your protonated alcohol, so that the OH bond will break and both of the electrons can go to the positive center of your oxygen atom. So we are reproducing our acid, okay, H3O plus, which is used as your catalyst, okay, as well as your alcohol. Okay, so you're making butanol. I'm going to leave you with exercise 2, okay, for your acid-catalyzed hydration, which you need to write down the mechanism for acid-catalyzed hydration of 2-methyl cyclohexene. Okay, so let's draw the structural formula for your 2-methyl cyclohexene. The cyclohexene means it has 6 carbon make up your cyclohexene. Okay, and there are methyl group on your carbon number 2. Okay, since it does not mention where is the position of double bond, so that means in this one 2-methyl cyclohexene means the carbon-carbon double bond is between carbon number 1 and carbon number 2. So it looks like this. Okay, so you need to propose a mechanism for acid-catalyzed hydration of this 2-methyl cyclohexene. Okay, so let me catch you with what are the expected product of this acid-catalyzed hydration. Okay, so you're going to make this alcohol. Okay, so thank you for watching. Bye bye.